Good morning, all of you. Welcome to Sri Jayendra Rank Zone. My name is Satish. I'm your chemistry faculty. Now so far we have completed 4 lectures in thermodynamics. Now fifth lecture I'm doing it now. It's a new topic based on enthalpies. So already we have seen in the previous lecture enthalpy of formation of a reaction. Now we are seeing new topic in this reaction now. So let us start now. So whenever the PPT is coming to you, please note it down. It's very, very important. All the PPTs, you have to maintain it like a classwork. So whenever you are seeing the video, so please take out your classwork and start doing it. Now, whenever you have seen the PPTs, please note it down as a notes. Now we are continuing with the new topic in this chapter. That is enthalpy of combustion we have seen. Next we'll see enthalpies of different enthalpy of solution. That is enthalpy of solution. So what is enthalpy of solution? Delta H of solution. It is defined as a change in enthalpy. It is defined as a change in enthalpy, that is change in heat energy, when 1 mole of a substance is dissolved in excess of water. So when 1 mole of a substance is dissolved in excess of water, so that further dilution does not produce any heat change. So it is called enthalpy of solution. So when 1 mole of a substance is dissolved, when 1 mole of a substance is dissolved in excess of water, it is called enthalpy of the solution. The change in enthalpy that is taking place when 1 mole of a substance is dissolved in excess of water is called as enthalpy of solution. Example, potassium chloride solid when dissolved in water, it forms potassium chloride aqueous. The enthalpy of solution is 4.4 calories. So, and in this case, delta H is positive, so it is endothermic process. So, enthalpy of solution can be exothermic or endothermic. That's why I want to tell you. So, since delta H is positive, so it is called endothermic reaction. So, potassium chloride when dissolved, solid potassium chloride when dissolved in water, it forms potassium chloride aqueous solution. It is called, and in that case, enthalpy of change in enthalpy is equal to 4.4 kilocalories. So that is endothermic reaction. And similarly, when copper sulfate solution is dissolved in copper sulfate solid when dissolved in water, it forms copper sulfate aqueous solution. So in this case, enthalpy of solution is minus 15.8 kilocalories. It means it is exothermic reaction. So by this, what you can understand, enthalpy of solution may be negative or positive, that is exothermic or endothermic reactions. So what is enthalpy of solution? I hope it is clear. So whenever a solute is dissolved in a solution, two changes taking place. That is either heat is given out or heat is absorbed, and that heat is given out is called enthalpy change, and that heat is called exothermic reaction when it is negative, that is heat is given out. When heat is absorbed, it is called endothermic reaction. I hope it is clear. So it is nothing but simple. The change in enthalpy taking place in a solution when 1 mole of a substance is when 1 mole of a substance is dissolved in excess of water. It is called as enthalpy of solution. I hope it is clear. Next, lattice enthalpy. It is very, very important. Lattice enthalpy, you'll see this in class 12 also in solid state, because usually for solids we have lattice enthalpy. So lattice enthalpy means dissociation is the enthalpy change produced. It is the enthalpy change produced when 1 mole of an ionic lattice. So already you know ionic solids. Ionic lattice dissociates into isolated gaseous ions. It is endothermic in nature. Always it is endothermic in nature. So sodium chloride, when you dissolve it in water, it forms sodium ions as well as chlorine ions. So that's why it is soluble in water. So when a solid is soluble in water and changes to its ions, gaseous ions, it is called as lattice enthalpy. That is the enthalpy dissociation. Here, sodium chloride dissociates to form sodium ion, sodium gaseous ion, and chlorine gaseous ion. And in this case, delta H is 786 kilojoules per mole. As it is given, plus it is endothermic in nature. So what is lattice enthalpy? The breaking up of an ionic solid in solution. The breaking up of an ionic solid in solution is called lattice enthalpy. The breaking up of ionic solid in solution is nothing but lattice enthalpy. And whatever the enthalpy change, that is the enthalpy change produced when 1 mole of ionic lattice dissociates into isolated gaseous ions, is called as lattice enthalpy. So in that case, whatever the energy change, it is called as lattice enthalpy, and it is endothermic in nature. I hope it is clear. Next, lattice enthalpy. Lattice enthalpy of formation. Here, two models we have. One is lattice enthalpy dissociation, and there is lattice enthalpy formation. It is an enthalpy change produced. So, in the formation, it is an enthalpy change produced when 1 mole of an ionic crystal is formed from its isolated gaseous ions. So it is a reversible process here. You can see when 1 mole of sodium ions and chlorine ions when combined together to form sodium chloride crystal. So it is called lattice enthalpy of formation. The energy change produced during this, that is energy is produced here. So it is exothermic in nature. So it is very important. Lattice enthalpy formation is exothermic and lattice enthalpy dissociation is endothermic. I hope it is clear. Lattice enthalpy formation is endothermic and exothermic, and lattice enthalpy dissociation is endothermic. So the same heat is given. So it is given out minus 786 kilojoules per mole. I hope it is clear. So this is the example I have given for lattice enthalpy formation as well as lattice enthalpy dissociation. Lattice enthalpy dissociation is endothermic process and lattice enthalpy formation, that is association, is exothermic process. I hope it is clear. So next, hydration enthalpy, very, very important. It is an enthalpy change produced. It is an enthalpy change produced. Produced means here itself we can say it is exothermic in nature. Exothermic. So it is an enthalpy change produced when 1 mole of gaseous ions dissolve in sufficient water to give an infinitely dilute solution. So when 1 mole of gaseous ions dissolve in sufficient water to give an infinitely dilute solution, this is called as hydration enthalpy. So here chlorine ions, when dissolved in water, it forms chlorine ions aqueous. It is enthalpy is minus 364 kilojoules per mole, means this much of heat is produced when chlorine gaseous ions is dissolved in water. So this is called hydration enthalpy. So when 1 mole of gaseous ions dissolved in sufficient water, the enthalpy change produced is called as hydration enthalpy to form an infinitely dilute solution. I hope it is clear. Next. So hydration enthalpy is always exothermic in nature. Relation between enthalpy of solution, lattice enthalpy, and hydration enthalpy. Very, very important. This topic is very important because they will ask based on the solubility. Dissolution of ionic solid in a solvent may be considered to be a two-step process. First step, it is dissociation of the ionic solid into gaseous ions, that is, which involves the lattice energy and it is endothermic. And hydration of these ions in solution, which involves hydration energy and is endothermic, exothermic. So hydration of these ions in solution which involves hydration, that is solvation energy, is exothermic. So it is a two-step process. First, dissociation of ionic solid into gaseous ions, first step, and which involves dissociation, that is lattice energy, and is also called endothermic process. And hydration of these ions, already I told you, hydration enthalpy is nothing but the ions in solution which involves hydration energy is called as exothermic in process because energy is released in this case. So these are the two steps, dissolution of ionic solid. So what? Let us see what is the relation between these two. So first, suppose you take XY is a solid like NaCl. So heat of dissolution, that is X plus ions and Y minus ions. So it changes when it is dissolved in water, it changes to sodium gaseous ions and sodium aqueous ion. And in this case, heat is liberated. Similarly, XY dissociates from X plus ions and Y plus ions. That is called lattice enthalpy. So this is called lattice enthalpy of dissociation. This is called lattice enthalpy of dissociation, and this is called lattice enthalpy of dissolution of heat of solution. And this unhydration enthalpy forms this aqueous solution. So simple it is. Just see here. First process, solid changes to lattice enthalpy, that is formation of gaseous ions. And these gaseous ions, when dissolved in water, that is hydration enthalpy, forms X plus ions and Y minus ions. On the whole, this is called delta H of solution, that is solvation enthalpy. So that is called heat of solution, heat of solution. So heat of solution is nothing but it is equal to lattice enthalpy plus hydration enthalpy. So simply I'll write here, heat of solution is equal to, because it is taking place in three forms, standard heat of solution, that is called dissolution. Standard heat of dissolution of a compound is equal to standard heat of formation of lattice enthalpy, that is dissociation of lattice enthalpy, plus standard heat of hydration enthalpy. So if you add these two, you'll get dissolution enthalpy. I hope it is clear. So this is very, very important. So heat of formation of solution, that is enthalpy change in the dissolution process is equal to enthalpy change of lattice enthalpy plus hydration enthalpy change. So I hope it is clear. Standard heat here, degree means standard heat of formation. So lattice enthalpy is nothing but dissociation enthalpy. Here X solid dissociates to form X gases and Y minus it is exothermic, and this is also exothermic. So on the whole it is an exothermic process. So heat of dissolution is always exothermic in nature. I hope it is clear. Next. So as I told you, the heat of solution is equal to delta H degree of lattice plus delta H degree of hydration enthalpy. So lattice enthalpy plus hydration enthalpy. Or by how you got this? By applying Hess law. That is Hess law. If the heat, if a reaction takes place in one step or several steps, the total heat is remains constant. So the total heat of the solution that is equal to delta 1 plus delta 2. I hope it is clear. So this is the process, very, very important. So always dissolution enthalpy can be calculated using the formula dissolution enthalpy or enthalpy of solution. Enthalpy change, standard enthalpy of solution is equal to standard enthalpy of lattice energy plus lattice enthalpy plus standard hydration enthalpy, standard energy hydration enthalpy. So standard energy change of hydration enthalpy. So I hope it is clear. So this formula is most important. So always, whenever a solution, a solute is dissolved in a solution, these are the two steps taking place. First, the solute changes into its gaseous ions. Then, by gaining hydration enthalpy, they change into aqueous gaseous ions. They change into aqueous gaseous ions. So this is nothing but aqueous gaseous ions formation. That is, solid changes to aqueous gas directly. We will call it as enthalpy of solution or enthalpy of dissolution. Delta H degree of solution is nothing but what? Enthalpy of solution. Enthalpy change of solution. Standard enthalpy change solution. I can write it here. Standard enthalpy change of dissolution or solution. Or we can say it is dissolution. And on the whole, it is exothermic process because it involves both exothermic process. Hydrogen enthalpy is exothermic, and this is endothermic process because dissociation bond is dissociating, so this is endothermic process. So previously I told it is exothermic, it is endothermic. So endothermic, exothermic. So it can be overall endothermic or exothermic. When it can be endothermic, exothermic, if this is greater than this, it is exothermic. If this is greater than this is endothermic. I hope it is clear. So if lattice enthalpy, if lattice enthalpy greater than hydration enthalpy, the dissolution process, lattice means at endothermic. So it is endothermic in nature. The dissolution can be endothermic. Similarly, if lattice enthalpy is less than hydration enthalpy, the process is exothermic. The dissolution process exothermic. So the dissolution process of a solution can be exothermic or endothermic depending upon the lattice enthalpy and hydration, because the dissolution, the heat enthalpy of solution is the enthalpy change of the solution is equal to sum of the lattice enthalpy plus hydration enthalpy. I hope it is clear. So this is very, very important concept. So please note it down in your classwork. I'm waiting for a second. So please note it down, all these points. Yes. Next. Determination of lattice enthalpy. How to determine lattice enthalpy? It is not possible to determine lattice enthalpy directly of ionic solid directly by experimental techniques. However, we can use the indirect method by constructing an enthalpy diagram called Born-Haber cycle. This Born-Haber cycle we have discussed in chemical bonding. In that topic itself, I told you what is Hess law. Also, Hess law we'll discuss in thermodynamics. I hope you remember. So in chemical bonding, we have discussed this Born-Haber cycle. It is taking place in several steps. So delta heat of formation of the reaction is minus, let us say, the net enthalpy of formation of NaCl is equal to, that is heat of formation of NaCl is equal to 4 minus 412, 411.2 kilojoules per mole. So sodium solid chlorine gas combines to form sodium chloride. This is actual reaction, but it takes place in several steps. It takes place in several steps. This Born-Haber cycle we have already discussed in this Born-Haber cycle we have already discussed in chemical bonding topic. So the overall process can be imagined to occur in the following steps. First, solid sodium changes to solid gases. That is enthalpy of sublimation. So standard enthalpy of sublimation is equal to 108.4 kilojoules per mole. So because it is called enthalpy of sublimation. Next, this sodium gaseous ion loses electron because solid sodium cannot lose its electron directly. So first, the solid sodium should be changed into solid gases. Sorry, sodium gaseous ion, sodium gas atom. So for this, we need sublimation energy because solid changing directly to gas, the process is called as sublimation, and the enthalpy change in the sublimation process is called as enthalpy of sublimation. What is it? It's called enthalpy of sublimation, and it is given as 108.4 kilojoules per mole. Next step is what? Second step. This is first step over second step. So this sodium gaseous ion is ready to lose its valence electron because sodium contains free electron and forms sodium gas ion by losing one electron. So that's why in the right hand side we are taking plus electron. So this is called enthalpy of ionization. Enthalpy of ionization because the amount of energy required to remove an electron from the valence, to remove the valence electron of a neutral gas atom, the amount of energy to remove required itself, it shows it is exothermic, endothermic. Here also endothermic, here also endothermic. So the amount of energy required to remove the valence electron of a neutral gas atom from the neutral gas atom is called as ionization enthalpy. So it is called ionization enthalpy of sodium. So let us take this. Next, chlorine. First, chlorine molecule should dissociate itself to form chlorine gas atom. So to form chlorine gas atom, it required bond dissociation enthalpy. That is called enthalpy of dissociation. So the bond should break up. So it is nothing but it is also exothermic because it is equal to 121 kilojoules per mole. So in that we have taken the values differently, but however values whatever it may be, the process is the same. I hope it is clear. So first step, second step, third step. Then what happens? Then ionization enthalpy. As I told you, electron gain enthalpy or ionization enthalpy. This chlorine gas is neutral sodium, this chlorine gaseous atom gains that electron which is coming from sodium and forms chlorine gaseous ion. In this case, enthalpy of electron gain enthalpy of chlorine. So this is called electron gain enthalpy. It is equal to, it is exothermic process, that is minus 348.6 kilojoules per mole. And finally, this sodium gaseous ion combines with chlorine gaseous ion to form NaCl solid. That is called lattice enthalpy. So lattice enthalpy of formation. So lattice enthalpy of formation, we can take all the addition of all these processes. That is delta H of sublimation plus delta H of ionization plus delta H of, so first what we have to do, delta H of sublimation plus delta H of ionization plus delta H of bond dissociation enthalpy plus delta H of electron gain enthalpy is equal to this. So delta 1 plus delta 2 plus delta 3 plus delta 4. Total 4 process if you do sum based on then delta H of formation. Then finally, this is delta H of lattice enthalpy and delta H of formation is given. So we can take delta H of formation is equal to this total plus minus lattice enthalpy. So from this you can find out lattice enthalpy also. So in this case we have done that only in the previous case. So delta H of formation for this reaction is equal to delta H of formation for this reaction is equal to delta H of sublimation first, delta H sublimation plus second step delta H of ionization, delta H degree of ionization enthalpy. Third step delta H of dissociation, delta H of dissociation di. Fourth step delta H of electron gain enthalpy, delta H degree minus delta H of plus delta H of lattice enthalpy, delta H degree of lattice enthalpy. So if you add all these things, you'll get. So if you want to find delta H of lattice enthalpy, delta H degree of lattice enthalpy. You can take because you know this value. So it is equal to delta H degree of formation minus this, take it as delta H1, delta H of sublimation minus plus all delta H of H degree of ionization plus delta H degree of dissociation plus delta H degree of electron gain enthalpy. So if you add all this and subtract from this, you'll get the answer of lattice enthalpy. I hope it is clear. Very, very important. So this already we have discussed in chemical bonding chapter by applying Hess law. So by adding this, as I told you, so delta H of sublimation plus delta H of ionization plus delta H of dissociation plus delta H of electron gain enthalpy plus delta H of lattice enthalpy. So if we take lattice, because we don't know this lattice enthalpy, we know heat of formation of sodium chloride, that is given minus 411.2. So minus of this minus addition of all these things, you will get finally minus 787.6 kilojoules per mole. I hope it is clear. So that's why ionization and lattice enthalpy is not taking in single step process. It's not easily find out from experimental data. We have to use by using Hess law only. We can find out by using Hess's law of constant heat summation. We can find out the determination of lattice enthalpy. Determination of lattice enthalpy by using Hess law only. We can find out determination of lattice enthalpy. I hope it is clear. Very, very important. So this we have already discussed in chemical bonding. If you want, you can refer the video of chemical bonding. Next, bond enthalpy of bond energy. Very, very important. The amount of energy required to break the bond, to break 1 mole of bonds of a particular type in molecules in a gaseous state is called bond enthalpy. So it is the amount of energy required to break 1 mole of bonds of a particular type in molecules in the gaseous state. For diatomic molecules, bond enthalpy is hydrogen molecule changes two hydrogen atoms. So bond enthalpy is equal to 435 kilojoules per mole. This is calculated value. Oxygen bond enthalpy is 428 kilojoules per mole. So to break one oxygen molecule into its respective atoms, we require this much of bond energy. So the energy required to break the bond, to break 1 mole of bonds of particular type in molecules in a gaseous state, is important, is called as bond enthalpy or bond dissociation energy or bond energy. Bond dissociation energy or bond energy. So this is called bond enthalpy. So whenever bond enthalpy is there, we have to take into consideration bond enthalpies also. Let us take bond enthalpies in polyatomic molecule. In a polyatomic molecule containing two or more bonds between the same set of atoms, like water, boron trifluoride, methane gas, carbon tetrachloride, etc., the energy required to break the successive bonds in a given molecule is not the same. Hence, the average bond enthalpy is used. So very, very important point here. So this is when we have a polyatomic molecule, we'll use average bond enthalpy for all these examples, for all these molecules, because they are not having similar atoms. Because in water we have two OH bonds. So in water we have two OH bonds. In boron trifluoride we have three boron trifluoride bonds. So in CH4 we have four CH bonds. In CCl4 we have four CCl, C single bond Cl bonds. So in the polyatomic molecule containing two or more bonds between the same set of atoms, the energy required to break the successive bonds in a given molecule is not the same. Hence, the average bond enthalpy is used. Why we are using average bond enthalpy? Because to break the successive bonds in a given molecule, the energy is not same. So that's why we are using average bond enthalpies in a polyatomic molecules. So, for example, in water molecule, the bond dissociation enthalpy of two OH bonds are not the same. As I told you, water containing two OH bonds, because the structure of water will be like this. This is one OH bond, this is one another OH bond. And these two bond enthalpies are not same. So, first, let us see. Higher water molecule changes to H plus OH minus ion. So it forms delta H1 is equal to 498 kilojoules per mole. And this OH changes to H plus and OH. So further, this is breaking up into H and O. So let us take delta H2. So bond dissociation energy of water is equal to 2H, that is delta H1 plus delta H2, it is 928 kilojoules per mole. And so by this you can say bond enthalpy of OH. So average bond enthalpy is 464, that is 498 plus 430 by 2. because since we have two bonds of OH bonds, so we'll take it as 464 kilojoules per mole. It is taken as 498 plus 430 by 2. In this way, we'll calculate average bond enthalpy. So this is called average bond enthalpy. So average bond enthalpy of formation of OH is taken as 464 kilojoules. Why we are taking by 2? Because it is divided by 2. Because in water we have average bond energy or average bond enthalpy. In water we have two OH bonds. So average we will take, that is OH bond enthalpy divided by 2. So to form OH bond enthalpy, it takes place in two steps, that is delta H1, delta H2. So we are adding that two and we are finding this. So this is an example for finding average bond enthalpy. I hope it is clear. So please note it down. Very, very important topic. Whenever they are given bond enthalpies, you have to take number of bonds. You have to take number of bonds. So similar for methane molecule, the bond enthalpy is CH4 changes to C plus 4H. Total it is 1664, and it contains, since it contains 4 CH bonds. How many CH bonds? 4 CH bonds, because the methane structure is C single bond H, single bond H, single bond H, and single bond H. Since it contains 4 CH bonds, so a bond enthalpy of CH bond is equal to CH bond enthalpy is equal to 1664 divided by 4. Total divided by 4, so it is 416 kilojoules per mole. So bond enthalpy of CH bond, how to calculate in methane? Divided by 4. I hope it is clear. Next, standard enthalpy of atomization of an element. Standard enthalpy of atomization of an element. It is an enthalpy change produced. It is an enthalpy change produced when one mole of a gaseous atom is obtained from its element in its standard state, that is 298 kelvins and 1 atmosphere. This is standard state. So enthalpy change produced when one mole of gaseous atom is obtained from its element in standard state is called enthalpy of atomization. So here the enthalpy of atomization, that is nothing but what? Carbon solid changes to carbon gas. Gas is carbon atom. It is called as enthalpy of atomization. It is equal to 170.9 kilocalories. It is calculated value. Similarly, enthalpy of atomization of hydrogen is 52.1 kilocalories, because hydrogen exists as diatomic molecule. So hydrogen atom should be taken as 1 by 2 hydrogen gas changes to hydrogen gas atom. So enthalpy of atomization. So to break up molecule into atom, we require heat. So that heat is called as enthalpy of atomization. To change the molecule into atom, we require some heat. So that heat is called as enthalpy of atomization, and it is endothermic process, because we have to give out some energy so that then only the molecule can break up into its respective atom. So this is called enthalpy. So simple words you can say, the changing of molecule into atom, the changing of one mole of a gaseous atoms is obtained from its element in its standard state is called as enthalpy of atomization. Standard change. Standard means at this temperature and pressure. I hope it is clear. Very, very important. Next, we'll see standard enthalpy of atomization of an element. Here, the enthalpy of atomization of carbon is same as its enthalpy of sublimation, because, so by this you can say, because enthalpy of sublimation also we have seen the same value. So enthalpy of atomization of carbon is same as its enthalpy of sublimation. So therefore we can write the enthalpy of atomization is equal to half into bond energy of hydrogen atom, half into bond energy of hydrogen atom. So this is the observed things from the given values. Now, enthalpies of reactions from bond enthalpies. The importance of bond enthalpies is in the calculation of enthalpies of gas phase reaction. So, in this case, very, very important to note down. Whenever they have given bond enthalpies in the reactions, whenever they are given, in the previous cases we have seen, they'll give a chemical reaction, they'll ask us to find heat of formation of reaction. But in that case, they have given directly formation of molecules. But if they have given individually bond enthalpies of all those things, we have to use the formula delta H of the reaction, that is enthalpy change of the reaction, is equal to sigma bond energy of reactants. Reactants we have to consider first, then sigma bond energy of products. So bond energy of all the reactants minus bond energy of all the products. So here, generally we'll do products minus reactants, but here we have to do bond energy of reactants minus bond energy of products. Whenever they have given bond energies, we have to use this formula. I hope it is clear. And whenever you are finding enthalpy of combustion, also one more important point I want to add here. Whenever you are finding enthalpy of combustion, automatically, even though you get plus value, you have to keep it as negative, because always combustion, enthalpy of combustion is exothermic process. Enthalpy of combustion is what? Exothermic process. So in that way, first in the previous lecture we have done one numerical. So in that we are taking minus value. So I hope it is clear. So bond enthalpies problems we'll do now. It's most important. Now, bond dissociation energies of hydrogen molecule, chlorine molecule, and HCl are given as 104, 58, and 103 kilocalories per mole respectively. So bond dissociation energy of hydrogen, bond dissociation energy of chlorine, and dissociation and bond dissociation energy of HCl are given this. Calculate the enthalpy of formation of gas. So simple it is. Straight away we can take. First, you write the balanced stoichiometric equation. Hydrogen gas combines with chlorine gas to form 2 moles of HCl gas. And for this, they are asking enthalpy of formation. Enthalpy of formation is equal to how much? Formation of HCl gas. So that they are asking. And they have given bond dissociation enthalpy of hydrogen 104. So bond enthalpy of hydrogen is equal to 104. And bond enthalpy of chlorine molecule, this is hydrogen. Bond enthalpy of chlorine molecule is 58. And bond enthalpy of HCl, for HCl, one molecule is equal to 103. So enthalpy of HCl is equal to 103. So simple, we can take sigma of bond enthalpies of reactants minus sigma of bond enthalpies of products. But here we have to take into 2, because 2 moles of HCl is formed. So 2 into sigma and bond enthalpy of products. So straight away we can take delta H of the reaction is equal to delta H of formation is equal to this. So that is equal to sigma bond enthalpy of reactants, that is 104 plus 58 minus 2 into 103. Simple it is. So 104 plus 58 minus 2 into 103. 2 into 103 is 206. And 104 plus 58 is 162. So 162 minus 206, it is minus 40 kilojoules per mole. Sorry, 162, that is 38 plus 6, 44. So 44 kilojoules per mole. It is minus or plus? It is minus. So enthalpy of formation of HCl gas is minus 44. I hope it is clear. So it is 22, because 2 moles for 2 moles. And for 1 mole, they are asking enthalpy of formation of HCl gas. So minus 44 divided by 2. So it is 22 kilojoules per mole, 22 kilocalories. Actually, it is kilocalories is given. So I have taken kilojoules. It is wrong. So only unit confusion is there. So it will take it as kilocalories per mole. It is as simple as like this. So why we are taking? Because for this total heat of formation is for total, it is 44 kilocalories per mole, because in the right hand side we have seen 2 moles of HCl, but they are asking for enthalpy of formation of only 1 mole of HCl gas. So for 1 mole, you have to take half of this is equal to 1 mole. Either way you can do. So finally you got answer 22 kilocalories. I hope it is clear. So the bond dissociation energies of hydrogen, chlorine, and HCl are 104, 58, and 103 kilocalories per mole respectively. Calculate the enthalpy of formation of gas. First, you write the skeletal equation. H2 plus Cl2 gives H2HCl. So heat of formation is equal to how much you have to find. Already they have given bond enthalpy of hydrogen molecule, bond enthalpy of chlorine molecule, and bond enthalpy of HCl. So sigma delta heat of formation of reactants is equal to heat of formation of a reaction when bond enthalpies are given. See here, whenever they have given bond enthalpies, we can write sigma bond enthalpy of reactants minus 2 into sigma bond enthalpy of first. Why 2? Because here 2 moles of HCl is formed. So that's why I have taken 2 into. Otherwise, simply you can use the formula sigma bond enthalpy of reactants minus sigma bond enthalpy of first. And 2 why you have taken here? Because 2 moles of HCl is formed. So straight away, sigma bond enthalpy of reactant. Reactants, what are the reactants? We have hydrogen, that is 104, and calories per mole, kilocalories per mole, and chlorine, that is 58. So 104 plus 58 minus 2 into 103, because bond enthalpy of HCl molecule is 2 into 103. So it is nothing but 162 minus 206, that is minus 44 by 2, because they have asked for one mole only, for 1 mole of enthalpy of formation of HCl gas. So it is for 1 mole only we have to take into consideration. So that is minus 44 by 2. It is equal to minus 22 kilocalories. I hope it is clear. Very, very important model this is. So many times they asked for NEET and JEE means. So please take into consideration very important point, that is sigma bond enthalpy of reactants minus sigma bond enthalpy of products when the bond enthalpies are given. Next. So some more questions I want to add based on this. So question number 2 now. Question number 2. Let us see question number 2 now. If at 298 kelvins, if at 298 kelvins, comma, the bond energies of CH, the bond energies of CH, C single bond H, comma, C single bond C, comma, C double bond C, and H single bond H are respectively, this previous question JEE is from this concept, are respectively 414, comma, 347, 615, and 435 kilojoules per mole. 435 kilojoules per mole respectively. The value of, calculate the value of, so the value of enthalpy change for the reaction. They're asking enthalpy change for the reaction CH2 double bond CH2, that is ethene, on reaction with hydrogen gas forms CH3 single bond CH3, that is ethane. So ethene changes to ethane gas at 298 kelvins and 1 atmosphere respectively. So answer first option, minus 250 kilojoules. Second option, plus 125 kilojoules. Third option, minus 125 kilojoules. And fourth option is plus 250 kilojoules. Plus 250 kilojoules. Now let us see this question. As I told you, whenever they are given bond enthalpies, so we have to see the reactants as well as products. So, and delta H of the reaction they are asking. So delta H of the reaction, standard enthalpy of the formation, is equal to sigma bond enthalpies of reactants, minus sigma bond enthalpy of products. So this we can take it as first sigma bond enthalpies of reactants. Let us take, so in CH4 bonds, how many? One C double bond C. So let us take in ethene molecule first, C double bond C, one C double bond C, and CH2 double bond CH2. So we have in ethene molecule how many? This is the reactant. So in ethene molecule, how many C double bond C? One C double bond C. So C double bond C is how much it is? First one, second one, third one, that is 615. Plus how many CH bonds? 1, 2, 3, 4 CH bonds. Plus 4 into CH bond. What is the bond enthalpy of CH bond? So it is C single bond C is not there. C double bond C. CH bond is how much? 4 into CH. That is 4 into CH bonds is how much? CH is 414. So 4 into 414 minus. So 4 into 414 minus. This is, this is plus again. This is first reactant. Second reactant, 2 HH bonds. So bond enthalpy of one HH bond is in hydrogen molecule, one HH bond is there. So 1 into HH bond enthalpy is given how much? This fourth one, 435. So plus 435. This is bond enthalpy of reactants minus bond enthalpy of ours. In bond enthalpy of ours, we have 1 CC bond, because in ethane molecule we have 1 CC bond, 6 CH bonds. So in ethane molecule we have, in ethane C2H6, we have 1 CC bond and 6 CH bonds. As place is not there, so I'm writing it here. Please note it down. So 1 CC bond and 6 CH bonds. So minus 1 into CC bond is how much? C single bond C is 347. So 1 into 347. I'm keeping bracket here. Plus 6 into CH bonds. How many CH bonds? 6. So each CH bond is 414. So 6 into 414. So if you do this calculation, 100%, this is called sigma bond enthalpy of products. Simple. Just we have to substitute, that's all. So numbers is only important. So 4 into 414 plus 435 plus 615 minus 1 into 347 plus 6 into 414. So 6 into 414 plus 347. So you'll get answer after substituting this. You'll get minus 125 kilojoules. So please verify this question. Very, very important. This model is very, very important. So please verify this question. It's most important. I hope it is clear. I'm waiting for you to copy down. So please copy down this question. Next question. Next question, I'm doing it now. So I hope it is clear. So these type of questions are most important. So first question we have done, second question also I have done based on average bond enthalpies. Next question, question number 3. Theoretical question based on this. The standard enthalpy of formation. The standard enthalpy of formation delta HF at 298 kelvins for methane, that is CH4, is minus 74.8 kilojoules per mole. Minus 74.8 kilojoules per mole. The additional information required. The additional information is also previous JMA's question. The additional information required to determine average bond enthalpy, average bond energy for CH bond, average bond energy or enthalpy, both are same, for CH bond. For CH bond, formation would be option 1, the dissociation energy of hydrogen, the dissociation energy of hydrogen, and enthalpy of sublimation of carbon, and enthalpy of sublimation of carbon. This is first option. Second option, latent heat of vaporization of methane. Latent heat of vaporization of methane, CH4. Third option, first 4 ionization energies of carbon and electron gain enthalpy of hydrogen. first four ionization energies of carbon and electron gain enthalpy of hydrogen. Fourth one, the dissociation energy of hydrogen molecule. Dissociation energy of hydrogen molecule. So these are the four options we have given. So first option, to find the standard enthalpy of formation of methane gas for methane is minus 74.8. So for this to find what is the additional information required to determine average bond energy for CH bond formation would be. So first we'll see carbon in solid form combines with hydrogen, 2 moles of hydrogen in gases form to form 1 mole of CH4. This you should know it. So for this we require carbon as well as hydrogen from water. So the additional information required for this is the bond dissociation energy of hydrogen, because hydrogen gaseous molecule changes to a gaseous atom, and enthalpy of sublimation, because carbon solid should change to carbon gas first step. So these two are required. So that's why answer is first option. Latent heat of vaporization, it is nowhere related with latent heat of vaporization of methane. And first four ionization energies of carbon and electron gain enthalpy of hydrogen is also not required. The bond dissociation energy of hydrogen, if alone hydrogen molecule is there, what about carbon? That also we should know. So the additional information required for this would be, the additional information required for this would be nothing but what? It is hydrogen, the bond dissociation energy of hydrogen, and enthalpy of sublimation of carbon. So both the things are required. I hope it is clear. So this is question number 3. So answer is first option. Next question, question number 4. So important models only we are discussing. So please note down. And with these models, you can do many questions in the normal questions also. So now very important question. The standard enthalpy of formation of ammonia. The standard enthalpy of formation of ammonia is minus 46.0 kilojoules per mole. It is minus 46 kilojoules per mole. If the enthalpy of formation of hydrogen, if the enthalpy of formation of hydrogen from its atoms, the enthalpy of atomization they are given from its atoms is minus 436 kilojoules per mole, minus 436 kilojoules per mole, and that of nitrogen is, and that of nitrogen is minus 712 kilojoules per mole, minus 712 kilojoules per mole. The average bond enthalpy of NH is, the average bond enthalpy of nitrogen single bond H is, in ammonia is, is also very, very important question. First option, option 1 is equal to minus 964 kilojoules per mole. Second option, plus 352 kilojoules per mole. Third option, plus 1050 kilojoules per mole. And fourth option, minus 702 kilojoules per mole. So these are the four options given. Very, very important question. So please note it down. First you note down the question, then I'll discuss the key also with this. So already we know enthalpy of heat of formation of ammonia. So they have given enthalpy of heat of formation of ammonia is equal to minus 46 kilojoules per mole. So from the reaction already we know N2 plus 3H2 gives rise to 2NH3. So it is 2NH3. N2 plus 3H2 gives rise to 2NH3. So bond breaking is endothermic and bond formation is exothermic. Assuming S is the bond energy of NH bond. Therefore, we can write simple directly. So 1 mole of nitrogen. So bond enthalpy of reactants is equal to heat of formation of reaction is equal to sigma of bond enthalpy of products. So reactants minus sigma of bond enthalpy of products. So simply you can take bond enthalpy of reactant is 712. So minus 712. So it is plus we have to take plus 2 into 436. Sorry, 3 into 436. Plus 3 into 436. And bond enthalpy of products it is equal to minus 2 into 46. So this is called formation of ammonia. So 712 plus 3 into 346. Why we are taking plus? Because assuming bond dissociation. And here they have given bond dissociation, they have given bond formation. So bond dissociation will be positive. So with this we are taking it as positive now. So let us see the calculation part now. So that is 712 plus 2 into 3 into 436. So 3 into 436 is equal to 1038. Sorry, 1308. So that is equal to 712 plus 1308 is equal to 2616 plus 2 into 46 minus 92 is equal to 2524. So bond enthalpy of 2524, 2524 kilojoules per mole. But we require for single NH bond. In ammonia, we know already ammonia, nitrogen has how many bonds? 3 NH bonds. So it is divided by, so nitrogen has how many bonds? 3 NH bonds. They are asking us for 1 NH bond. So it is nothing but divided by 6. Why? Because total we have 2 moles of ammonia. So that is 2524 divided by 6. So 2524 divided by 6 if you take into consideration 2524 divided by 6. Why are taking divided by 6? Because it is nothing but, so it is approximately plus 352 kilojoules per mole. So answer is plus 352 kilojoules per mole. So I hope it is clear. So this is the answer to find average bond enthalpy of ammonia and H bond. So total they have given, and they have given for bond enthalpy of formation of hydrogen, bond enthalpy of formation of even this is also given, that is nitrogen. So in that bond dissociation energy, we should take it as plus plus plus. So 712 plus 3 into 436 minus 2 into 446. When they have given bond enthalpy of reactants minus bond enthalpy of products. So finally it is coming as 2524. It's coming as how much? It is coming as 2524. So that 2524 can do it the calculation part easily. So this calculation part totally you have find for the entire reaction formation of ammonia, but it is forming for 2 moles of ammonia. For 1 mole it is divided by 2, and in that we are divided by 3 because 2524 divided by 2 or 2524 directly divided by 6 I am taking, because it is equal to 352 kilojoules per mole. So I hope it is clear. So answer is 352 kilojoules per mole. In this way, you can find average bond enthalpy. Average bond enthalpy of NH bond in ammonia. Total, we are getting 2 moles of ammonia. So it has, in 1 mole of ammonia, we have 3 NH bonds. So in 2 moles, we have 6 NH bonds. How many NH bonds? 6 NH bonds. So bond enthalpy of NH is average bond enthalpy is equal to NH bond length by 6. That is total formation of ammonia by 6. I hope it is clear. So this is very, very important question. So with this, we are ending up this session. And in the next session, we'll do more questions based on this. I hope it is clear. So please follow the class properly and do more new types of same types of numericals you'll find in the entrance book.